So we know now how to deal with problems, absolute value problems that involve equations to solve. So then, of course, we're in Module 3. We also have to think about what happens with inequalities. So what do we do with greater than signs? What do we do with less than signs? And I've got a couple of blank boxes down here for us to record our findings, because it turns out that we end up needing to do something different if we have a greater than sign and an absolute value versus if we have a less than sign and an absolute value. In both cases, there's a splitting that happens. We're going to split each case into two inequalities, but the difference is in how we combine those two inequalities together. So that's what we need to get to here. Let's start with the first example. Absolute value of 3x minus 12 is greater than 3. So what did you do to begin the process of solving this inequality to find out what values x may have? So our first step here, because there's no additional algebra outside the absolute value bars for us to get rid of, according to reversing the order of operations, the first thing we need to do is get inside the absolute value bars by making the absolute values go away. So our first step, just like it was in the last example, our first step is to split. And when we do that, we're going to get, in the splitting process, one inequality which has 3x minus 12 and 3 as they are. Another inequality which has 3x minus 12 and negative 3. So that aspect of the splitting, negative 3. That aspect of the splitting is just like it was when we saw it with equations. And is going to be the same no matter whether we have a greater than sign or less than sign. So star and minus star. And same story if I have a less than sign. But it's what happens from there that gets more interesting. Cool. So if I have a greater than sign here, what I'm really looking for is those values of x for which the distance of 3x minus 12 from 0 is greater than 3. So what I'm doing there is I'm saying I want my 3x minus 12 quantities to be at least 3 units away from 0. That means they could be 4 units away. They could be 6 units away. They could be 100 units away. They could be 1,000 units away. So there's a lot of possibilities for how far away from 0 my 3x minus 12s are. Right? It gives me this wide, open-ended, unbounded interval. And those wide, unbounded intervals can continue both on the positive side and on the negative side of the number line. Right? If all I know is that I need to be at least 3 units away from 0, it's like there's a 3-unit force field sitting around 0 that I can't get any closer to 0 than that, but I can be as far away as I want to. Right? So what we expect in this situation is that we get one inequality which bounds our distance from 0 on the bottom side, another one which bounds it on the top side. So the first thing we notice is that the inequality symbols in these two inequalities after we split, the inequality symbol reverses when we reverse the sign of the right-hand side. So that's the first new thing that happens in these problems. So we have to reverse the sign when we reverse the inequality sign when we reverse the negative sign. And then the other piece, and this ties us back to what we were talking about on Monday, is that if what I know is that I need to be at least 3 units away from 0, that means that I could be on one side, on the negative side of the number line, with my 3x minus 12, or I could be on the positive side of the number line way over here. And either one of those two possibilities will lead me to a solution of this compound inequality. So the connective element that makes it a compound inequality in the case of a greater than sign, and I need to see who write this down when you do these problems, is the word or. So in the case of absolute value and a greater than sign, we get a compound inequality connected with an or. So greater thans become ors. And as you might expect, for similar reasons, well, really opposite reasons, less than signs become ands. Because if we're constraining the absolute value to be less than something, it's saying that we want the distance from 0 to be within a certain amount of distance. So I can't get as far away as I want to because my distance is constrained. I have an upper limit on it. And so I need to both, in the case of a less than sign, be less than the quantity, but also greater than the opposite of the quantity. I need those both to be true. And so in a less than sign case, we end up with an and instead of an or. This is definitely a conversation you'll want to revisit when this video gets posted at the end of class and you're working on these problems. These are the trickiest problems in all of Module 3, which puts them in the running for the trickiest problems in the whole first half of the course. You'll want to look back at this conversation again. This is really, it's heady and it's very easy to miss a step in logic along the way. Let's finish up this example. We have a compound inequality with an or. How am I going to solve this? What are my next steps?
So
yeah.
The equal signs is no or and.
So if I'm going to solve this compound inequality, we'll solve each of the pieces in the way that we know how. Right? Add 12 to both sides, then divide by 3 on both sides, because this first one's going to then be 3x is greater than 15. 3x is less than negative 9. Then divide by 3 on both sides. Divide by 3, divide by 3, divide by 3. X is greater than 5, x is less than negative 3, and then don't lose along the way this all-powerful connective, the word or. Because
negative 9 minus 3 plus 12 is then positive 9?
It very much is, and thank you for the correction. Yes, that is my bad. Divide that by 3, and then I get x less than 3. Thank you. Yep, that was a sign error on my part. See, I do it too. Okay, so far so good, but again, we can't stop here, right? Unlike when we're solving an equation that has two answers and then we can just sort of stop and say those are my two answers, we have an opportunity to combine these two inequalities into one, and that or that sits in between them is the key to doing that. So let's phrase our answer using interval notation, which is almost always how Alex has you answer these problems, and so it's a good habit to get into regardless. So here's my number line, 1, 2, 3, 4, 5, 6. So 3 is here, 5 is here. Those are really the only numbers that we need to mark in this example. And just like we did on Monday, what we'll do is look at these two pieces separately. So let's have a purple piece and an orange piece. And we'll graph each one of those in its own turn. So if x is greater than 5, how do I graph that on my number line? So we talked about this on Monday. I would graph that by putting an open circle at 5. Open because 5 is not included because this is strictly greater and not greater than or equal to. Ditto for x less than 3. Open circle at 3 because 3 itself is not included because less than. And shade to the left. So there are each of my two pieces. And what do I do with my two pieces when I have an or that connects them? How do I combine these two into a single set? And we'll draw that single set in, let's say, blue on this picture. As a single set, which of these two pieces do I take? In order to be a solution of this compound inequality, which of these two inequalities do our solutions need to solve? Purple or orange? So for example, x equals 6. Does x equals 6 solve this compound inequality? Is it true that 6 is greater than 5 or that 6 is less than 3?
Oh, yeah.
Yeah, why?
Well, it's greater than 5.
Because it's greater than 5. Because it belongs to the purple set, it's a part of our solution. So if I'm sketching my solution in blue here, I'm going to sketch a piece that includes the purple set for sure. What about the orange one? Why not? 6 is not less than 3, but it is greater than 5. So because 6 belongs to the purple set, it belongs in our solution. It's true, it's a true statement to say 6 is greater than 5 or less than 3. That's a true statement because 6 is greater than 5. Right? As soon as it belongs to one of these sets, it belongs to the or disjunction of those sets. So that means not only that the purple piece is part of our solution, but what else? The orange piece is also part of our solution. So 0, for example. Is it true that 0 is less than 5 greater than 5 or less than 3?
Yeah.
Yeah. Because why? Because it's less than 3. Because it belongs to one of the two sets, it belongs to the or disjunction of those two sets. So when you take an or, you take everything, right? Rather than just looking at the overlaps, which is what we do when we do an and instead. So our blue set here, we've sketched on the number line, is the solution of this inequality. How would we write it as an interval? We've got two pieces here. What would be interval notation for the leftmost piece? What's the leftmost extent of this interval? How far to the left does it go? Infinity. Right, what kind of infinity? Negative infinity. It's at the left side of the number line. How high up does it go, this piece? 3. So the first piece, negative infinity, comma 3. What kind of brackets? Round or square? Round on the negative infinity because always. Round on 3 because why? Because 3 is not included. Round bracket, open circle, strictly less than. Right? Those three things occur together. Ditto with our piece on the right. How far to the right does it go? Infinity, always round bracket. How far to the left does it go? Round bracket or square? Round bracket again because 5 is not included. Open circle, strictly greater, round bracket. What's the last thing I need in my notation to convey that these two pieces are part of the one set which answers our question? And instead of writing the word or, in notation we'll use the union symbol. Union is just the set theory way of representing that we're sticking these two pieces together to form a single set, which is our answer. So that capital, it's not really a capital U, it's a stylized U. It doesn't have like I was saying on Monday, it doesn't have this, it doesn't have this going on. It's just a plain old sans serif capital U for union, which is a part of your Alex math palette anytime that a problem like this comes up. So find it on the screen rather than trying to type it in as a U on the keyboard.